Okay, let's move into 6.1 and 6.2. Okay, sounds good. Yeah, I didn't see what you were talking about when it came to the tables and stuff. Okay. So 6.1 is on functions of several variables. Okay, basically multivariable functions. Okay, so a function of two variables f of xy assigns one output for each input pair xy. Okay. So we have, this is our inputs, and then our outputs are f of xy. Okay, so we plug in the x and the y, and we get out a value. Oftentimes this is called z. Okay. So we would say that we have a triple value here, a point and three space of x, y, and z, but it's based on a function, f of xy. Okay, so you could say, like, for example, f of xy would be equal to, say, x squared plus y squared, right? And then for a certain value of x and y, say 1, 1, I would get 2 out, okay, or x, y, z. 1, 1, 2. Okay. Basically, I would say f of 1, 1 is equal to 2. Okay. The inputs would be the 1, 1, and the outputs would be the 2. Okay, let's look at example 1 here. For the function p of xy equals 4x plus 6y, find p of 25, 10. Okay, well, all we're going to be doing is plugging in the 25 and 10. Okay, so that's going to be 4 times 25 plus 6 times 10, right? And so 4 times 25, that's 100. 6 times 10 is 60, and so that's 160. Okay, let's look at a business example. Total cost. Okay, the total cost to a steel company and hundreds of dollars is given by, C of X, Y, Z, W. Ooh, they got a lot of costs. Is equal to 4x squared plus 5y plus z minus the natural log of w plus 1. Okay. So we're going to say, well, what are all these cost values here? Where x is labor cost and labor. Y is materials cost. Okay. Z is advertising costs. And W is machinery costs. Okay, so we want to find C of 3, 2, 1, 10. So here, all we're going to do is plug in.
Ordered.
Is there a question? Okay. All we're going to do is plug in these values into this multivariable equation. So let's do that. 4 times 3 squared plus 5 times 2 plus 1 minus the natural log of 10 plus 1. Okay. So this is going to be 4 times 3 times 3. That's 4 times 9 plus 10 plus 1 minus natural log of 11. Okay. So that's 36 plus 10 plus 1. That's 11 minus natural log 11. So that's going to be 47 minus natural log of 11. Okay, and we could leave it like that. However, we really want this in thousands of dollars, right? The answer to be in thousands of dollars. Is it thousands of dollars or hundreds of dollars? It's hundreds of dollars. So we want this to be in hundreds of dollars. Okay. So I'm going to find my decimal equivalent of this. 47 minus natural log of 11. Okay, 47 minus 11 natural log equals, and that's 44.6020 21. 44.6021. 44.6021. Okay, so if I multiply this guy by hundreds of dollars, right? Multiplying by the hundreds of dollars. Okay, so that 44 is now 4,400. So multiply by 100, we get 4460.21, or $4,460.21. Okay, so what does this mean? This means that when I had $300 in labor, $200 in materials, I had $100 in advertising, and $1,000 in machinery. Okay, machine, I can't spell. Okay, machinery costs. When I have this and I plug it into this formula, I get out those values here for the total cost. This is the total cost. Okay. Okay, let's look at the domain of some of these functions here. Okay, number 3 here. Find the domain of the following functions. Okay, so we're looking for what is x and what is y this time. Remember, y is in the domain of f of x, y. So we're looking for both, okay? Z is the range. F of x, y is the range. And x and y are both in the domain now. So is there any restriction on what x could be? So x could be anything I want it to be. There's no restriction. So here's how I write the domain. Okay, the same goes for y. Y has no restriction either, which means that the range is unrestricted. Well, the range is restricted. We're just going to deal with the domain for right now. Okay, the domain cannot be a negative number because if I plug in a negative number for x, it goes positive. If I plug in a negative number for y, it still goes positive. So I'll always end up with a positive output. Okay, but the domain for x and y, okay, it's not just x that's in the domain, it's x and y. Because remember, think of this as z. Okay, we plug in our x's and y's. So if we look at, remember our function machine, okay, what we're doing is we're plugging in x's and y's, and we're getting out z's, okay, or f of x, y's. And in here is my what is happening to my x's and y's. How are they being manipulated? Well, in this case, we're squaring x's and squaring y's. Okay, so I wanted to say, is there any restriction on what x and y can be? No, there's no restriction on what x and y can be here. And so I just say that this goes from negative infinity to x to positive infinity, and y is the same thing, negative infinity to positive infinity. Okay, and that's the domain of that guy. Now, let's do one where there is a restriction on the domain. Okay, and let's see what that restriction is. Okay. So we say f of x, y is equal to the square root of 1 minus x squared minus y squared. Okay, so now is there any restriction on what on what x and y can be? And so what I'm going to do here is I know that I can't get a negative under the square root. Okay, so this cannot be negative. Okay, so this has to be greater than or equal to 0, right? So I can say, 1 minus x squared minus y squared has to be greater than or equal to 0, because I can't take the square root of a negative. So I'm going to subtract 1 from both sides. Okay. I'm going to get negative x squared minus y squared is greater than or equal to negative 1. Now I don't like all these negatives. So what I'm going to do is I'm going to divide through by a negative, or multiply through by a negative. Negative 1. Now the rule is when I multiply both sides of an inequality by a negative, I have to reverse the sign. So this becomes x squared plus y squared less than or equal to. Okay, the sign gets reversed when I multiply by a negative. Is less than or equal to 1. Okay, well, what is this? What is this? Well, we could say that the domain here is that x squared plus y squared has to be less than or equal to 1. It means that whatever x is, it can't be more than 1. Okay, whatever y is, it can't be more than 1, but the combination of the two also can't be more than 1. Okay, so we're going to say that the domain for x and y is x and y such that, this little line means such that x squared plus y squared is less than or equal to 1. Okay, and this equation, x squared plus y squared less than or equal to 1, okay, that it's very similar to this equation, x squared plus y squared equals 1. Okay, and this equation is the equation of a circle. Of radius 1. Okay. And so if we want everything that's less than or equal to that circle, then what we do is we don't get a circle. What we get a circle. The outer edge is the circle of radius 1. You could say that this thing is a circle of radius 1. That red circle there is a circle of radius 1. But if I talk about x squared plus y squared is less than or equal to 1, then all of my then could x be 0? Yeah, it could be x could be 0. Could y be, say, 1/2? Sure, y could be 1/2. The sum of that is still less than 1. So anything inside this circle will work. So we can say that the domain is we don't call this a circle anymore because the circle is just the outside edge. We call this a disk of radius 1. This is a disk of radius 1. Domain is a disk of radius 1. Did you want something? Sorry, I have somebody spying on me, but it's all good. I don't think they think that I actually have a job. I think they think that I just sit in my room and talk to myself all day. That's what they think at my house. Like Dad doesn't really have a job. He just pretends to have a job. He's talking to some imaginary people on his computer. Okay. Some of that might be true, a little true, and I'm just talking to myself. Okay, I see you, Oscar. Why don't you turn that YouTube off, okay? Pay attention. Okay, 6.2, partial derivatives. Okay. Giselle's paying attention. That's good. So at least I got one student that's tracking with me. At least for the jokes. She's in it for the jokes. She's like, I could care less about all this other stuff. I'm just here for the jokes. And the free food. Well, there used to be free food. Oh, that's good. That's good. See, now, just tell people, tell people that there's free food, and then they'll wake up and they'll be like, huh? What? See, no, there's no free food. I was just trying to get your attention. That's too much paperwork, Oscar. I know who's passing the class and who's not passing. That's my roll call right there. No, honestly, what's the Zoom takes roll for me on actually. Pretty nice that way. Okay, so let's talk about partial derivatives. Okay, for z equals f of xy. Okay, so this is why we talked about this before. Okay, z of f of xy. The partial derivatives with respect to x and y are okay. We say f sub x, okay, which is the partial with respect to x, and f sub y which is the partial with respect to y. Okay, so f sub x is the partial with respect to x, and f sub y is partial with respect to y. So what does this mean? Okay, so f sub x, it can also be designated as dz dx. Okay, these aren't d's, these are not Arabic d's, they're Latin d's. Okay, it looks like that. Okay, just for different notation. It means take the partial on z with respect to x. Okay, the partial of z with respect to x, or the partial of xy. You could do this as well. Partial of f with respect to x. Okay, so just saying, look, it's saying fix y as a constant and take the derivative on x. Okay, so we want to fix y as a constant. Just treat y as a constant. Okay. F sub y, same thing. It's dz dy. Okay, which is equal to the partial of f of xy with respect to y this time. What does this tell me to do? This tells me to fix x as a constant, or treat x as a constant. And really doesn't matter. You could just go treat if that makes more sense to you. Okay, treat x as a constant. And take the derivative on y, okay, or of y. Okay, of y. So let's see how this works. Okay, so number one. Okay, for z equals x squared plus y squared, let's find f sub x and f sub y. Okay, so it's saying, look, take the derivative of z, but only with respect to y, or with respect to x, treat y as a constant. Well, what's the derivative of a constant? If I treat this as a constant, yeah, the derivative of a constant is 0. So what does this become? This becomes 2x plus 0, which is just 2x. Okay, so that's the partial. We said this is the partial derivative of x, okay, or on x. Okay, f sub y, same thing, right? So what's this one going to be? Well, this one, if we take the partial of y, we're going to treat x as 0, or x as a constant. Okay, so now this guy's a constant. And so it's just 0 plus 2y, exactly, very good, which is 2y. And so this is the partial derivative of y. Okay, so we can say that f sub x is equal to 2x and f sub y is equal to 2y. Okay. Okay, let's try another one. Okay, for f of xy equals 3x squared y plus xy squared, find the partial of f with respect to x and the partial of f with respect to y. Okay. So f sub x, okay, let's take the partial with respect to x first. Okay, that means treat y as a constant. Well, what happens to y here when it's just a constant? Well, it becomes part of the coefficient. So this really is just 3 times y, right? Because y is treated as a constant. It's not treated as a variable. So it's going to be 3 times y times the derivative of x squared, which is 2x. Plus, and then what happens when I take the derivative of this thing? This is just a constant y squared times the derivative of x, which is 1. So this thing comes out to be 6xy, okay, plus y squared. Okay, so that's the partial with respect to x. Okay, oops. Let's do the partial with respect to y. Partial with respect to y. Okay, now we treat x as the constant and y as the variable. Okay, so if x squared is the constant there, it just becomes 3x squared. Y is a variable, so it's times 1. Derivative of y is 1. And then we have x. Remember, x is a constant, so it's just the coefficient. And then times 2y. So this guy becomes 3x squared plus 2xy. That's the partial of on y there. Partial with respect to y. Okay, let's try another one of these. F of xy is equal to e to the xy plus y natural log x. Okay, let's find f sub x. What's the partial with respect to x here? So we have to treat x as the variable. Okay, but y is as the constant. Okay, so this is like, think of it as like e to the x times 3, right? And what would that be? That would be e to the 3x. So if I want to take the derivative of this, it would be a chain rule. Derivative of the whole thing is e to the 3x times the derivative of the exponent, which is 3. Okay, so let's see if we can use that logic over here. And we want to take and the whole thing, right? The whole thing becomes the derivative times the derivative of the exponent, which is y times x. Well, what's the derivative of y times x? If y is a constant, it's just y. Okay. Okay, plus y times the natural log of x. Again, y is the constant here, the coefficient. So this is y times the natural log of x. What's the derivative of natural log of x? It's 1 over x. So we get f sub x is equal to y e to the xy plus, I can write this as y over x. Okay, let's look at f sub y here. What's f sub y going to be? Well, it's going to be the exact opposite of what we got before when we did the e to the xy. It's e to the xy, but now it's going to be times, well, what? The y is the variable and the x is the coefficient. So yeah, it's going to be x, exactly. Plus this is going to be the derivative with respect to y now. Well, that means the natural log of x is just a coefficient. It's just a number. Natural log of x is just a constant. Treat it as a constant. And then what's the derivative of y? The derivative of y is 1. So f sub y is equal to x e to the xy plus natural log of x. Okay, so why do we need to know this? Okay, well, there's something called the, in business, okay, there's something called the Cobb-Douglas function, production function. Okay, so the Cobb-Douglas production function, this came out about 100 years ago. Okay, it looks like this. It says P of xy is equal to A times x to the little a, maybe I'll use b in this case. I don't want too many a's. X to the b times y 1 minus b. Okay. Okay, where p is of units. Where p is the number of units produced. X is labor units. Y is capital units. Okay, or units of capital, I should say. Or units of capital. Okay, and this function is to generate the gross production for like a country. Okay, so you have units of capital and you have units of labor, and we want to know, right? And also take note that the exponents, okay, b plus 1 minus b equal 1. Okay, so they add up to 1. Basically, this guy, the exponent of this guy and the exponent of this guy will have to be decimals, right? And those decimals will have to add up to 1. So, for example, if b was equal to 0.25, then 1 minus b would be 0.75, right? So you get to raise to the 0.25 and then 0.75. Okay, so we say that the partial with respect to x, okay, yeah, they always will equal 1, exactly, yes. So the exponents will always add up to 1. And a is just an initial amount. We don't have to get into that. Okay, dp dx, okay, is the marginal productivity of labor. Okay, and dp dy is the marginal productivity of capital. Okay. Okay, so let's see what's going on here. So let's do an example. You can label it. Oh, it's example 4. Oh, okay. Okay, so let P of xy equal 50 to the 2/3, oops, 50 times x to the 2/3, y to the 1/3. Okay. A. Find the number of units produced okay, with 125 125 units of labor and 64 units of capital. So 125 units of labor. And generally, like if you're thinking like this as a country or like, you know, a small state, I mean, sorry, a large state like California, you're thinking in terms of like millions of units, right? So this is, you know, they would be like, oh, it's 125 million units of labor, 64 million units of capital, then, you know, what's the units, number of units produced? That would be like in millions. Okay, we're just going to keep it simple. We're just going to say 125 units of labor and 60 units of capital. Okay, so what are we going to do? We're just going to plug that in. P125 and 64. Okay, so P of 125, 64 is equal to 50 times 125 to the 2/3 times 64 to the 1/3. Okay. Okay, so my bad. Sorry, I hit the wrong key. So 125 to the 2/3, that's 125 to the 1/3 squared. 64 to the 1/3. Now I know that 125 to the 1/3, the cube root, is the same as the cube root of 125. And this is the cube root of 64. And those are nice values. Okay, the cube root of 125 is 5. So this is 5 squared. And the cube root is 64. That's also nice. Okay, they purposely gave us nice numbers. That's 4. So this is going to be 50 times 4, which is 200, times 5 squared, which is 25. And that's going to come out to be 5,000 units. Okay, 5,000 production units. Okay, when I have 125 labor and 64 capital, I get 5,000 production units by just plugging in, basically. Okay, so B, okay, so let's find the marginal probabilities here, or find the marginal productivities. When x equals 125 and y equals 64. Okay, so we want the PDX. Okay, well, what was the original function? The original function was P equals, what was it? It was 50x to the 2/3, y to the 1/3. And so we want the partial with respect to x. So we want P sub x. Okay, that means that y is treated as a constant. So let's just put that in front. Okay, and then we want to take the derivative of this thing. Well, the derivative of that is going to be 2/3 times x to the 2/3 minus 1. Okay, so this is going to be 50 times 2/3, which is 100/3. Okay, times x to the negative 1/3. Okay, times y to the 1/3. Okay, that's that y to the 1/3 here. So this really becomes 100 over 3 times y to the 1/3 over x to the 1/3. Okay, And maybe I'll leave it like that. Okay, I could put it all under 1/3 if I really wanted to, but I think it's just going to be easiest to leave it like this. Okay. So now what's P of y? P of y is going to be 50. Okay, x to the 2/3 is the constant. Y to the 1/3, that's going to be 1/3. Y to the 1/3 minus 1. This is going to be 50 over 3. Okay, times x to the 2/3 times y to the negative 1/3. Okay. And so this becomes 50 over 3 times x to the 2/3 over y to the 1/3. Okay, I'll leave that like that. So the last thing I want to do is just evaluate this. What are the marginals when x is 125 and y is 64? I just plug in the 125 into this, and I'm going to say this is 100 over 3 times y. Y was 64 to the 1/3 over 125 to the 1/3. Okay, so this is 100 over 3. 64 to the 1/3 power. That's the cube root of 64. And this is the cube root of 125. So the cube root of 64 is 4. This is 4. The cube root of 125 is 5. Okay. So this ends up being, I could cross cancel here. Okay, the 5 and the 100, that becomes 20. So this becomes 80 over 3. Okay. Or if I divide 3 into 80, that's 72 goes in. 3 times, that's 375 goes in, okay? And 78 would go in evenly. So 78 would be 78 divided by 3 would be 6. 72, that would be 24, 25, 26. So this is 26 and 2/3. Okay, if I divided that. So it's 26 and 2/3 production units per, okay, because this marginal is a derivative. It's a rate of change per labor units, because it's based on changing x, the changing x's. Okay, so it's a rate of change. Okay, P sub y, okay, is going to be 125/64. That's going to equal 50 over 3, x to the 2/3. So x was 125 to the 2/3, all over 64 to the 1/3. Okay, so this is 50 over 3. We saw what 125 to the 2/3 was before. You can go back. Okay, it was right here when we just evaluated 125 to the 2/3 end up being 25. Okay, we follow that all the way down. So this is 25 over 64 to the 1/3. That was 4. Okay, and so we just get this is 25 over 2. 25 times 25 is 625 over 6. I messed up. Right. Oh yeah, this is not negative 1/3, I'm sorry. This is negative 2/3. This should be 2/3. Sorry about that. So this is not. So this should be 64 to the 2/3. So that's 4 squared, which is 16. Okay, and so then this becomes 625 over 40 over 24. This is going to get reduced by 2. So that's 24. So 24 into 625, that is 26 and 1/24 production units per capital units. Okay, or production per capital. Okay. I should say probably not per labor units. I should say, because per is like per labor. I mean, that's fine. Production units per labor unit. It should be per labor unit because it's per labor. It's per 1 unit of labor. How many production units are changing versus how much does 1 labor unit change? And how much do the production units change per 1 capital unit change? Okay, basically what this is saying is it's saying when capital is fixed at 64 units. Okay, so capital is fixed at 64 units, and we're just going to vary the labor. Okay, labor changes, capital does not change. Okay, that's what the partial with respect to x is. Okay. Then a 1 unit change in labor from 125 to 126 will cause approximately a 26 2/3 unit increase in production. Okay, so just saying, look, if we fix the capital cost and we go from 125 to 126, how much is the labor, how much is the total production going to change? Well, it's going to change about 26 2/3 units. Okay, well, what happens if we fix labor cost? When labor is fixed at 125 and we just vary, okay, we fix labor and we just vary capital, okay, then a 1 unit change okay, from 64 to 65 change 64 to 65 capital units will produce about a 26 1/24 change or increase in production units, in total production units. Okay, and what a lot of companies, or what a lot of a lot of economists, I can't even talk today. Okay, economists. What a lot of economists will do is they'll actually say, oh, okay, let's use the Douglas-Cobb function, but then they'll create a table, right? They'll say, oh, okay, for P of 125.64, this is the P 125.64 table, right? And they'll say, oh, okay, we're gonna fix, you know, say that you know, this is the labor and this is the capital, right? And they'll be like, oh, okay. So if I change labor and capital, say that if I fix, say the labor costs at 125, right? But actually, I should not do that. It should be just fixed at 125. Right, so 125 up there, right? Okay, and then we'll fix the capital at 64, right? Okay, so we already know what this is, right? We know what this is. This was 5,000 units, right? So 5,000. Okay, and we'll talk about the, you know, how much is it changing, right? From this 5,000. Well, if I go up to 65, but I fix it as 125, right? Well, that's going to be my, if I fix the x but change the y, that's going to be my p of y, right? So this would be like, right? This would be like p sub y, right? Because what is that going to tell me? That's going to tell me this is about 50/26, okay? And 1/24th, okay? Point something. Okay, but what if I change the 64, or sorry, say that I change the labor cost to 126, but I fix the capital of 64, we're going to fix on this one. Okay, 64, then we go to 126. This is also about 5026. So you can create a whole chart like this, doing your partials. Okay, so because this is going to be the partial with respect to x, right? So we would get, these are my partials with respect to x. These are all my partials with respect to y. Okay, and you get a chart and say, well, if I manipulate this one way or the other. Okay. Okay, let's talk about higher order partials. Okay, what happens when we take partials of partials? Ooh, fun stuff. Okay, partials of partials. Okay. Well, let's look at f sub x and f sub y, right? F sub x and f sub y. Okay, so what did we say f sub x was? This is the partial of x, right? Partial of x, or with respect to x. Okay, and then this is the partial of y. So now with f sub x, I have two choices. I can say, well, let's take the partial of f of x again. That's f sub x x. Okay, or we could take the partial of x and then take the partial of y. So this is the partial of x of the partial of x. Okay, it just means take the partial of x and then do it again. Okay, partial of x of the partial of x. Okay, and then you would say, well, take the partial of xy, right? So you would take the partial of x, it goes in order, take the partial of x We would say take the partial of y of partial of x. Why is that kind of written backwards? Well, because we're saying take the partial of y of the partial of x. It would be like kind of, in a way, saying we're going to take the partial of the partial, right? The partial of y of the partial of x, right? So take the partial of y of the partial, find the partial of x first, and then get the partial of y. Okay, so that might be more confusing. Partial of the partial of x. So anyway, with y, we have the two choices as well. We can say take the partial of y and then the partial of x, and then the partial of y and then the partial of y. If f is continuous, then you know what happens? Then f of xy equals f of yx. It doesn't matter which order I take the partials. I could take the partial of x and then y, or I could take the partial of y and then x, and I should always end up with the same result. Okay, so let's find our partials here. Let's say that f of xy this is number 5, by the way. F of xy is equal to x squared y cubed plus x to the 4th y plus x e to the y. Okay, now I want to do first I have to find my partial with respect to x and the partial with respect to y. Okay, so let's find our partial with respect to x. Well, what's that going to be? Treat y as a constant. Okay, and then just take the derivative of x. Well, that's 2x y cubed plus, this is going to be 4x cubed y plus, y is my constant, so e to the y is treated as a constant, so this just becomes plus ey, because the derivative of x is 1. Okay, f sub y, now let's do it with respect to y. Okay, so this is going to be x squared is treated as the constant times 3 y squared. Put the 3 in front. Plus x is treated as a constant. This is going to be x to the 4th. Okay, because this is just derivative of y is 1, so that goes away. Plus, okay, x is the constant, and then e to the y. Well, what's derivative e to the y when we're taking y as the variable? It's just e to the y. That just stays the same. Okay, so now what do we want to do? We want to take, first we want to do our partial of x with respect to x. So now we're going to take this thing and we're going to do we found our partial of x, which is this guy, f sub x. So now we want to take the partial of x again with respect to x. Okay, so this is going to be 2 times y cubed. Okay, 2 times y cubed, because the derivative of x is just 1. Okay, this is going to be plus 12x squared y, because again, y is a constant here. Okay, plus 0. Okay, that just becomes plus 0, okay, which is equal to, well, I can just get rid of it, it's 0. Okay, so that's f of xx. Okay, f sub x. Okay, what about f sub xy? Take the partial with respect to x, and then now take the derivative with respect to y, not x. Okay, the derivative with respect to y, treat x as a constant, 2x, and then that's going to be 3y squared. So this really becomes 6xy squared. Plus, okay, derivative with respect to y, though, well, it's just 4x cubed, the x is constant. Okay, and then plus e to the y. Now it's with respect to y. So that's e to the y is just e to the y. Okay, that's nice. Okay, let's do f of y with respect to x. Do you want to do x first or y first? Let's do y first. Okay, let's do y. Okay, so this. I'm just going to bring down the 2 from the y squared, derivative of y squared. That's just going to be 6x squared y. Okay, plus x to the 4th with respect to y, that's just 0. Plus, okay, derivative of this thing with respect to y is itself again. Okay, just x e to the y is just x e to the y. Because the x is a constant or a coefficient, and then the derivative of e to the y is e to the y. So I can rewrite this as plus x e to the y. Okay, so that's partial of y with respect to y. And then the partial of y with respect to x. Okay, let's see if this works out. That ends up being the same. Take the partial of y and then do the derivative with respect to x. Well, that would be 6x y squared. Okay. Plus 4x cubed plus, okay, derivative with respect to x is just going to be e to the y. That's the constant. And so lo and behold, look, these two are equal. Okay, so on Tuesday, we will go over the last section, which will be section 6.3, and we'll be actually utilizing these